All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is calorimetry problems. You're going to need a calculator for this one, so if you don't have one handy, go ahead and pause the video and we'll get started. This is one that I think will divide into two parts because the second half in particular is pretty involved. So let's just take 5 on this one and then we'll do 5 more on the next one. Number 1 says, what is the specific heat of aluminum if the temperature of a 28-gram sample of aluminum is increased by 8.1 degrees Celsius when 207 joules of heat is added? So let's kind of visualize what's happening here. We've got this aluminum block, let's just say it's got a mass of 28.4 grams, and we want to apply 207 joules of heat to that block. So when we put 207 joules of heat into the block, the temperature increases, and it, obviously, and it increases by 8.1 degrees Celsius. We want to know the specific heat of the block. So the formula we're going to use is Q equal mc delta T, and we're going to do just a little simple algebra to isolate the C, the specific heat. So the C, or the specific heat, is going to be Q divided by M divided by delta T, and then we'll just plug in. We get 207 joules applied, and the mass was 28.4 grams, and this is an 8.1 degrees Celsius temperature change. When I do that math, I get 0.89984. Let's talk just a little bit about significant digits. I can only have 2 because of the 8.1 right there. This 9 will kick this 9 up, and that 9 will kick that 8 up. I get 0.90 joules per gram per degree Celsius. That's my final answer for number 1. Let's go on to number 2. Number 2 says this. Number 2 says, what is the specific heat of silicon if the temperature of a 4.11 gram sample of silicon is increased by 3.8 degrees Celsius when 11.1 joules of heat is added? Essentially the same problem as number 1. This time it's just a different substance. Same formula, Q equal mc delta T. Let's isolate the C. We get C is equal to Q divided by M divided by delta T. Let's just plug in now. We've got for the Q, the heat added is 11.1 joules. We'll divide that by the mass, 4.11 grams, and divide again by the temperature change, 3.8 degrees Celsius. I get 0.7107. Let me go to two significant digits. The 0 will not kick that 1 up, so we just get 0.71 joules per gram per degree Celsius, and that'll do it for us for number 2. Let's move on to number 3. Number 3 says, how much heat must be added to 8.21 gram sample, it's an 8.21 gram sample of gold, to increase its temperature 6.2 degrees Celsius? They tell me the specific heat of the gold is 0.13 joules per gram per degree Celsius. Exactly the same formula. This time we're going to solve for Q. So we'll just plug in. We have Q is equal to mc delta T. Q is equal to, the mass was told to us to be 8.21 grams. Specific heat 0.13 joules per gram per degree Celsius. And the temperature change was 6.2 degrees Celsius. It's just a matter of plugging values in. We want two significant digits. When I multiply across, I get 6.6 joules of heat that needs to be applied to achieve that temperature change of 6.2 degrees Celsius, and we're done with number 3. Let's go on to number 4 now. Number 4 says this. Number 4 says, if 40.5 joules of heat is added to a 15.4 gram sample of silver, how much will the temperature increase by? The specific heat of the silver is 0.235 joules per gram per degree Celsius. Again, very simple. Use the formula Q equal mc delta T. This time we're looking for how much the temperature increase will be. So we're going to solve for delta T. So Q is equal to, or I should say Q divided by M divided by C is equal to change in temperature. Just plug in now. Q is 40.5 joules. We'll divide that by the mass. We'll divide that again by the specific heat, and we get this number. 11.2 degrees Celsius is what that temperature increase would be, and we're done with number 4. Let's go on to number 5. Here we go. Number 5 says, when a 25.7 gram sample of sodium iodide dissolves in 80 grams of water in a calorimeter, the temperature rises from 25.0 degrees Celsius to 24 degrees Celsius. Calculate the delta H for this process. Now let's visualize what's happening here, okay? So we've got this equation. It's sodium iodide, it's a solid, and it's going to dissolve into sodium ion plus iodide ion, and we want to know the delta H. Now, there's a couple of principles that are involved here. The first one is this idea of a calorimeter and what a calorimeter means. So let's talk a little bit about what we mean by calorimeter. A calorimeter is nothing more than an isolated container that holds in it some amount of energy, and it's separated from the remainder of the environment, or what we call the universe. So everything inside of the container, everything inside of the calorimeter, we call the system. Everything outside we call the universe, right? That's the remainder of the universe. So the system is inside. Let me just label that system, just like that. And so what is happening here is that sodium iodide plus sodium, or yields sodium ion plus iodide. That's inside the container. Outside the container is water. All right, so all around the container is water. So let me just draw that as, I'll just draw it as little green dots, just like that. So if you can imagine water completely surrounding this system where sodium iodide is being dissociated, right? And so what's happening here is that heat is leaving the system, it's leaving the reaction and going into the water and heating up the water, right? It's heating up the water. Now, because of that, I know that this is an exothermic reaction. Exo means out, therm means heat. So that means this. It means if I can figure out how much heat is being absorbed by the water, I'm going to know the delta H, or the amount of heat being released by the system or by the reaction. The reason is because of the first law of thermodynamics that says that energy can't be created, it can't be destroyed, it can only be transferred. So the energy that's generated by this reaction is going to have to be transferred, and none lost, but transferred to the water, and that's going to be the energy that's going to heat up the water, right? That's what's going to heat up the water for us. So if I want to know the delta H, I simply determine the amount of energy, or the amount of heat absorbed by the water. I'm told that I've got 80 grams of water, so I'm going to start with 80 grams, times the specific heat of water is 4.184 joules per gram per degree Celsius. I just got that off of a chart. There's no other way to know that except just to get it off the chart. I'll give it to you on quizzes and exams. You don't have to remember it, but it is 4.184 joules per gram per degree Celsius for the water. And then the temperature, remember, went from 20.5 to 24.4. And by the way, temperature change, or delta T, is going to be always final temperature minus the initial temperature. So the final temperature was 24.4. It said it went from 20.5 to 24.4. So that's the final temperature, that's the initial temperature, and that's degrees Celsius. When I do that calculation, I get this number, 1,305.4 joules, right? Now remember, that's not the delta H, because this is an exothermic reaction. That's the amount of heat that was liberated by the reaction. That means that I'm going to have to report my delta H as a negative 1.31 kilojoules. I made it into kilojoules by divided by 1,000. But the important thing is that I put a negative sign there just for the purpose of the fact that it is an exothermic reaction. Heat is being lost by the system into the surroundings, right? From the system into the surroundings. The system plus the surroundings is called the universe. But because it's being lost, I'm going to give it, the delta H, a negative value, right? A negative value. So what I really could say is that sodium solid is being dissociated into sodium ion plus iodine ion plus heat, right? Plus heat. And that's the heat that's being used to heat the water. So if I figure out how much that heat is, which I've done, I know the magnitude of the delta H, and I just put a negative in front of it because it's exothermic. And we're done with number 5. I think we'll do another one on this one, and then we'll go ahead and go on to part 2 on the next video. Number 6 says, when a 16.9 gram sample of sodium hydroxide dissolves in 70 grams of water in a calorimeter, the temperature rises from 22.4 to 86.6 degrees Celsius. Calculate the delta H for this process. This is going to be exactly the same. In fact, this is an exothermic reaction. Once again, I know that because I'm going from 22.4 to 86.6, increasing temperature. That means that this reaction is generating heat. It must be, since the water surrounding it is increasing in temperature. That makes it an exothermic reaction. So Q is equal to delta H, at least in terms of magnitude. Again, at the end, I'm going to place a negative in front of the magnitude because of the fact that I know that it is exothermic. But at least in terms of magnitude, remember the amount of heat that was liberated by this reaction. Because in this reaction, we're going to get, in addition to these two products, we're also going to get heat. That's what's heating up the water. And so the delta H then is going to have a negative value. So let's determine how much heat the water absorbed. Q is equal to M times C times delta T. The mass of the water, we're looking at it from the water standpoint, is 70.0 grams. That's how much water was heated. The specific heat is 4.184 joules per gram per degree Celsius. Again, that's from a table. And then the final temperature, remember, was 86.6. The initial temperature, 22.4 degrees Celsius. When I do that calculation, I get 18,803 joules. That's 18.8 kilojoules. I just move the decimal place over 3 places to the left. Remember that this is an exothermic process for the reasons that I've just spoken about. So when I write the answer, I'm not going to forget to put that negative sign there. I'm going to report my answer as negative 18.8 kilojoules. That'll do it for this problem. I'll see you on the next video. Thanks. Bye-bye.